Hello, this is Austin, and I was going to go over the book Practical Digital Processing by Mark Owen. And in chapter 2, there's some questions here. So the very first question, it talks about, it says, a cosine wave of frequency f is sampled. You know what? I'm not going to read it. Basically, in short, uh, this, and these three formulas or equations, I guess you want to call it, I don't know. They should all be the same no matter what k is. No matter if k is negative or positive for any integer k. And t is time, so t is the sample number times 1 divided by sample rate. So I'll just rename n sample number. I mean I. Just to make it a little more clear, I guess. Yeah. So this is kind of what aliasing looks like. All these frequencies should spit out. All these, those should spit out the same numbers. All three, A, B, and C. So we can see here that they're pretty close. I mean, for each sample number here. Very close. The thing is yeah, the precision might, cause it to be a little off, but all three of these numbers are generally pretty close. These three are the same. Yeah. It's kind of crazy how that works. But then question 2, it talks about, gets a little bit more into aliasing, and it wants you to make a 400 hertz. I mean, another question in the chapter 2 talks about making a 400 hertz sine wave. Making a sine wave sampled at 400 hertz, 3200 kilohertz. So making a 400 hertz sine wave sampled at 3200 kilohertz and trying to play it back, but then zero out some of the samples. And we want to zero them out so that we can reduce the sample rate by 2 kilohertz. So 2000 hertz. So what I did to do that is here in reactor again. I'm just going to save this. So I just made a sine wave. So did a logarithm to change frequency to pitch, 400 hertz, set the amplitude. Then I routed this sound. Routed this sound from reactor into an audio channel. And then just recorded it, with record, press record here, just recorded it for 1 bar. It does look like it has a fade, doesn't it? It does have a fade. I think that's what this thing means. Is there like a show fades? It looks like it's automatically fading if I play it back. Let's see. Yeah, it has a little bump. And this is still playing. If only there was a way to remove the fading. Well, anyways, that's not that big of a deal. So I sampled that for 1 bar at 120 hertz. Went to here, went to export, changed it to 3200 hertz, exported it. Back in the reactor here, I put that sample in the sample map, sine wave at 400 hertz, 3200 sample rate, 120 BPM. So I changed my sample rate to 3200 kilohertz. And in order to get this ramp OSC to play 1 bar, I took tempo info, which is beats per second. So there's 2 beats per second. We want to figure out how many beats are in a bar per second. So if we divide by, so a beat is a quarter note, right? So if we divide that by 4, it should give us how many beats are in a bar, which would give us the frequency for the ramp OSC to keep oscillating at 1 bar at 120 BPM right here. Boom. Yep. And then, yep, I told you that I put my sample in that sample map. These are just oscilloscopes to look at the original 400 hertz and the aliased version. So this top half here in core is just the original 400 hertz running for, you know, looping over 1 bar. The bottom half is what I do is I just take the samples coming in, and every 16th sample, I am only playing every 16th sample. That's how, because it told me to reduce the sampling rate by 2 kilohertz. So then that's, so if I take, what is it, 3200,000, 32,000 sample rate divided by 16, that gives me 2,000. So I'm reducing it by 2 kilohertz. Wait. Yeah, I'm reducing it by 2 kilohertz. Yep. Like the book said. So boom. And then that's in this one. And then I put, you know, the left ear is the original sound. The right ear is the alias sound. So this is the original 400 hertz just playing back. That's this right here. And then this is the aliased, which is this top thing that looks all blocky. And to me, it sounds more like the original, but here's like just a test sine wave right here at 1600 hertz. So what's happening when you reduce the alias of this, reduce the sampling rate by 2 kilohertz, like I just did, is you get aliasing, and it turns out to be 1600 kilohertz. 1600 hertz, I mean. So if I play this sample sine wave, this test with the aliased, you see they sound pretty similar. Also, like I can change the aliasing. So I can, instead of aliasing by 200 hertz, I could go to 2000 hertz, I could go to 1000 hertz or 500 hertz. That's really strange how I divide by a bigger number, but reduce by a smaller amount of hertz. I don't think that's right. Huh. And I don't really understand how this gets to 16. It must be, because that sounds awfully similar. But yeah, that's my best trying to show off an example of how to do what it said in the book. This is my pretty good attempt, but now I'm confused on why you would divide a number by a bigger number and get a reduced by a smaller amount of. That's the only way I can think of, is reducing it by 200 kilohertz. It's just playing every 16th sample. Yeah. Well, anyways, I was deep in thought for a second trying to think about it. Yeah. Those are some of the questions in the book.